In this next lecture segment, we're going to talk more about atomic masses and moles. So the mass of one atom of carbon-12 is defined to be exactly 12 atomic mass units, AMUs. So the atomic mass is going to be that we see in a sample of an element is the weighted average of the isotopic masses of the element's naturally occurring isotopes. You usually don't have just one isotope of an element. There's a range of isotopes that are possible. And they're mostly evenly distributed in the environment. If we have a sample of carbon, it's going to be more or less the same percentage of carbon-12 and carbon-13. That's not entirely true. There are some imbalances, for example, in differences between living matter and dead organic matter, and that can be used for carbon dating by looking at the ratio of the masses and some subtle changes there. So, but usually when we're looking at the atomic table, we assume that we're getting things over a fairly even natural distribution. So if we look at the periodic table, usually you'll see an atomic number, the symbol for that element, and the atomic mass, that weighted average of all the different isotopes that can occur. So you might look at this for a second and say, wait a minute, I came back from before. A proton is 1.007 AMU, a neutron is 1.009 AMU. So if I take 6 protons and 6 neutrons, which is what makes up carbon-12, you get 12.096. And that is not 12.00. And it turns out that difference is due to the nuclear energy of the protons and the neutrons combining. When they combine, the total energy drops. And when it does, it means the mass drops as well. So you can see that E equals MC. So that difference is literally the mass due to the energy there. So that's, I think, a really deep, fascinating thing. But when it comes down to actually, once they're assembled, if you have 12 neutrons, if you have 6 neutrons, 6 protons together, they will always have the same mass. And we define that as the exact amount of 12 AMU. Why one atom of carbon-12 is opposed to being 12 AMU as opposed to one atom of hydrogen being exactly 1 AMU? That's a little more complicated, and there's some historical reasons. But once we pick a reference to define the unit AMU, then we can measure everything else in those terms. Okay, so that's why you can't get the total mass just by adding up the number of protons and neutrons. There's energy involved as well. Okay, so atomic weight, the average of the isotopic masses weighted by the natural abundance. For example, carbon is pretty much just carbon-12 and carbon-13. There are some other isotopes, but you don't see very much at all, and therefore, if you're calculating the weight, they contribute negligibly to the weight. Certainly, if you have a whole mole of atoms, there's going to be some C14 in there, but there's so little that it doesn't actually affect the total mass. So the mass of carbon-12 is going to be 12.00 AMU, defined by definition. The mass of the C13 is 13.003. There's that 0.003 is due to that extra energy term there. And carbon is mostly carbon-12, 98.89%, and then 1.11% carbon-13. And so if we're looking at the total mass, then we'd multiply the 12 times its fraction of abundance. You don't multiply it by the percent, you multiply it by the fraction, plus 13.003 times the abundance of carbon-13, and that gives you your 12.011. And this is actually one reason why we don't really look at we don't use more than 3 or 4 significant digits for atomic masses, is because you can get slight discrepancies of isotopes from sample to sample. But generally, 4 to 5 significant digits, pretty much all samples of carbon will be about the same. Okay, so let's look at an example for this. So let's do an example for relative abundance. So boron occurs naturally as the mixture of 2 isotopes, boron 10, which has a mass of 10.01 AMU, and boron 11, which is a mass of 11.0 AMU. If the atomic mass of boron is, as you can see on a periodic table, is 10.81, what's the relative abundance of boron 10? How much boron 10 is there versus boron 11? Well, what we can do is set this up as a math problem. We can use that same formula for relative abundance, but now we're going to, let me reset this for red. Okay, now we can say that you have a mass times abundance plus mass times abundance equals 10.81. So we know that the mass of boron 10 is 10.01, and its abundance, we don't know. 10.01 times X plus the mass of boron 11, well, 1, and what's its abundance? Well, if we assume that there's only 2 isotopes that are contributing, we know that the total abundance, that the fractions have to add together till 1. So we get 1 minus X equals 10.81. And now at this point, we've taken a physical problem and turned it solely into a mathematical problem. Now all we have to do is solve for X. So just doing the algebra a little explicitly this time. A lot of times we won't do the algebra into quite as much detail. When X equals 10.81. And now we need to gather the terms. We need to move this over to this side. And once we subtract that from both sides, and then we can just combine the x's, we get minus 1.00x equals minus 0.20. So clearly x is just 0.20. So what is x? So x is the relative abundance of boron 10, which means that the relative abundance of boron 11 is just 1 minus x, 0.80. So that's, you can have somewhat more complicated problems like this. For example, you could have 3 atoms and you'd be given the abundance of 2 of them. Or for example, you could be given the abundance and the mass and have to figure out the mass of the individual isotopes. Now, you know that if you see, boron 11, it's probably 11, but you don't know exact plus or minus something. You don't know what that something is. So those are the sorts of problems you can have. So so that's the sort of questions you could look at in terms of atomic mass and how the atomic mass comes about, having these, weird numbers that are not exactly ones when you know that the individual isotopes themselves are just combinations of integer numbers of protons and neutrons. Okay, so then let's take a look at Avogadro's number, atomic masses in the mole. So we define a number: 1 mole of any substance contains 6.022 times 10 to the 23rd 4 millunits. It's basically a number conversion factor. You can have a mole of marshmallows, a mole of atoms, a mole of molecules, a mole of whatever. It's just a number. There's nothing inherently molecular about a mole. In this picture, you've got a mole of several different substances, which are different amounts of substances, but they're the exact same number of atoms, of molecules of that substance. You can have a mole of moles. What would happen if you were to gather a mole, the unit of measurement, of moles, the small fluid critter, in one place? So you can check out that link. The link will be active in the PDF. It's rather gruesome, so I recommend checking that out. So the molar mass is the mass in grams of 1 mole of any element. Its value is equivalent to the atomic mass, but not the unit. So the molar mass so for example, 1 atom of carbon-12 is 12 AMU, and 1 mole of carbon-12 is exactly 12 grams. So that's the conversion factor we use. And that's essentially how Avogadro's number was picked. Avogadro's number was picked to be a useful conversion factor between single atoms and the amount of stuff that you can actually measure in the lab. So it's very convenient to just have at a molecular level, the AMU is the logical unit. At the macroscopic level, an amount like 12 grams. I mean, you could have come up with Avogadro's number to be the conversion factor between 1 AMU and 1 kilogram. I mean, you could have done that. But this is the choice we made. And it's easier to deal with 12 grams than 12 kilograms of substances. So that's what it is. It's just a nice conversion factor to go back and forth between the molecular scale and the physical scale that we interact with day to day. Yeah, so to get a sense of how big moles are, there's a lot of good examples in the book, but the best one is checking out the the number of moles. What happens if you get a mole of moles together? Okay, so that's what we want to be doing. A lot of times we're going to be using, we're going to be going back and forth between the number of moles, because if we're dealing with something at a chemical reaction scale, we need to know we're dealing with things at the level of single atoms, and we need to be able to convert back from that into the macroscopic scale, what we measure in lab. So here's an example question. Should be straightforward, but just to review everything. How many moles and how many atoms in silicon are in a sample weighing 10.53 grams? The atomic mass of silicon is 28.0855 AMU. Okay, so if we know what the atomic mass of silicon is, it means we actually know what the molecular mass is as well, right? Because the molecular, that's the mass of a single atom. And so then if, let's actually switch to this view mode, then 1 mole of silicon is equivalent to 28.0855 grams. All right, so if we have 10.53 grams of silicon, then if we're to convert to moles, the conversion factor of moles is 28.0855 grams of silicon. Sometimes it can be useful to actually be explicit. This is the conversion factor between grams of silicon and 1 mole of silicon. There's a different conversion factor between 1 gram of hydrogen and 1 mole of hydrogen. So at this point, we can cancel out the gram silicon. We can see our answers clearly in mole of silicon, and it's 0.3749 moles. Moles of what? Silicon. Mole is just a number, so we need to know number of what. Okay, and how many atoms are in that? So now that we have the number of atoms, we can say, well, 0.3749 moles of silicon. Then from 1 mole of silicon to that has exactly 6.022. A mole is an amount, and so that's equivalent to 6.23 times 6.022 times 10 to the 23rd atoms. Atoms of silicon. So that's, again, an exact conversion factor. 1 mole of silicon is exactly equal to 6.022 times 10 to the 23rd atoms of silicon. Is Avogadro's number an exact number? Not really. We only know it out to 7 or 8 digits, because then beyond that, it's beyond our limits of measurement. We can't actually sit down like with tweezers and pull out exactly that many atoms of silicon and weigh it exactly much. I mean, it's really dependent on our ability to measure masses, which we can only do up to 7 or 8 decimal points. So in theory, Avogadro's number is exact. In practice, it's highly precise, but still a little uncertain. For most cases, the atomic weight is going to limit our numbers of significant digits anyway. Okay, so do the calculation. Moles of silicon cancel out, and we get 2.258. And it looks like, yeah, we got 4 significant digits. So we know the answer to 4 times 4 significant digits. Let's write it a little smaller. 2.258 times 10 to the 23rd atoms of silicon. So we're doing this very slow here because we'll be doing these, we just want to practice it. We'll be doing these conversions throughout the entire process. So this is what you want to be practicing as you go through, that you can do these, in just a step or two, because they're an integral part to essentially all the sorts of calculations we'll be doing later, going back and forth between chemical reactions and large-scale chemical processes. All right, that's it for this lecture segment.